Hello everyone, my name is Zeping Yu. Today I'm going to introduce our work in EMNLP 2024. The title is Interpreting Arithmetic Mechanism in Large Language Models through Comparative Neuron Analysis. Arithmetic ability is an important skill of LLMs, which can affect the reasoning ability. If we can understand the mechanism of arithmetic task, we can design methods to enhance the reasoning ability. Previous methods have explored the information flow using causal mediation analysis. They found that shallow FFN layers process the inputs, then attention layers transfer the information to the last position. At last, deep FFN layers generate the outputs. However, layer-level information flow is not enough for understanding the mechanism. Many studies have found that the attention head and FFM neurons are the basic units storing different abilities, and it is essential to understand the neuron-level information flow in order to apply the findings on neuron level. Here are the achievements of our work. We locate the important attention heads and FFM neurons in both shallow and deep layers. We find the four stages during information flow, which are feature enhancing, feature transferring, feature predicting, and prediction enhancing. And we find that the shallow FFN neurons are hidden interpretable. At last, we analyze LoRa and find that LoRa enhances the ability by enlarging the FFN neurons' coefficient scores. We also apply the findings for model pruning and model editing. Before introducing our method, let me introduce the background shortly. In decoder-only LLMs, each layer's output is the direct sum of the layer input, attention output, and FFN output. This is named the residual stream. Another background is the definition of FFN neurons. Each FFN layer has two MLPs. The number case subvalue is the number case column of the second MLP, and its corresponding subkey is the number case row of the first MLP. The FFN output can be regarded as a weighted sum of many FFN subvalues. The coefficient scores are computed by the inner product between the subkeys and the residual output. Previous studies found that many FFN subvalues and subkeys are interpretable when projecting in unembedding space, which means multiplying the subvalue or subkeys with the unembedding matrix. Our method has four steps. First, we mask each head and compute the accuracy decrease in arithmetic operations in order to find the important heads. We find that there are a few heads playing very large roles. For example, the 22 head on layer 17 is very important for addition and subtraction operations. All the 1-digit to 3-digit accuracy drop much, so this head stores the 1-digit memorization. Then we propose the comparative neuron analysis method to identify the important neurons in deep FFN layers affected by the arithmetic head. We added the 22 head on layer 17 by replace the head's parameters with 0 and calculate the change of the importance scores on each deep FFN neuron. Specifically, the importance score of each neuron is the log probability increase in unembedding space caused by this neuron. If a neuron is affected by the arithmetic head, the importance score of this neuron should decrease a lot. We first apply this method on the case 3 plus 5 is with the final prediction 8. The identified neurons have very good interpretability when projecting in unembedding space. Their top tokens are related to the prediction 8. We also apply this method in all the 1-digit cases and find that the accuracy decreases 100% when zero editing the top 100 neurons. A more surprising finding is that when we only keep the top 100 neurons and mask all the other neurons in deep FFN layers, the accuracy only decreases 4%. This indicates that the important neurons are very concentrated, and model pruning at neuron level is possible. Then we find a prediction enhancing stage among deep FFN neurons. we compute the inner product between the lower neuron's subvalue and the upper neuron's subkey, and find that the inner products are very large. So the lower neurons can activate the upper neurons. We also locate the top 100 neurons in all one-digit cases and intervene the lowest neuron among these neurons. We find that the sum of the neurons' coefficient score drop much. This result can prove that the prediction enhancing state exists. Until now, we have explored the arithmetic head and the deep FFA neurons, but the roles of the shallow neurons are not explored. It is much harder to locate the shallow neurons because these neurons don't contain the information about the predictions directly. We analyze the case 3 plus 5 is 8 and calculate the inner product between the transformed shallow FFA neurons and the important deep FFA neurons. We find that the shallow FFA neurons are not directly interpretable when projecting into unembedding space. These neurons' attention transformation are interpretable. For example, the number 2072 FFA neuron on layer 12. This neuron is related to the input 3, and the other neuron is related to the input 5. We name this phenomenon hidden interpretable. And we also find that the word embeddings are also hidden interpretable. This phenomenon is because all the shallow neurons need to be transformed by attention layers before transferring into the last position. We design a zero-shot method to locate the hidden interpretable neurons. We compute the upper attention layers transform of each FFA neuron and project them into unembedding space. If the top tokens are related to the input number or operators, we add this shallow neuron into a neuron set. At last, we mask the neurons in the neural set and compute the accuracy decrease on all one-digit cases. The accuracy drops much. So this can prove that the hidden interpretable neurons are very important. Based on this analysis and results, we can construct the internal logic chain for the case 3 plus 5 is 8. First, in shallow layers, there is a feature enhancing stage. The hidden interpretable shallow FFA neurons related to the input tokens are activity. Then these enhanced features are transformed into the last position. The arithmetic head takes all the enhanced features as input and activate the deep FFA neurons related to the final prediction 8. Among the deep neurons, the lower neurons activate the upper neurons during the prediction enhancing stage. Then we apply the comparative neuron analysis method to explore the mechanism of LoRa. We add LoRa on the 9th attention layer and compare the important neurons between the original model and the LoRa model. And we find that LoRa enhances the accuracy by enlarging the important neurons' coefficient scores. In other words, the deep FFA neurons can be regarded as learned features. LoRa learns how to enlarge the features rather than learning the features in the LoRa parameters by themselves. And we apply our method in model pruning. In previous analysis, we find that the accuracy is not affected much when pruning many deep neurons. Based on this finding, we propose a method for model pruning. We first find the important neurons and prune the other neurons in deep layers. Then we add another LoRa and fine-tune it. This method can get very good accuracy. We also use the comparative neuron analysis method for reducing gender bias. We compare the neuron's importance score under different input cases. For example, we compare the cases a woman works as a nurse and a man works as a nurse. The neuron's importance scores are different under these cases because the probability is not the same. Using this method, we can locate the gender bias neurons and reduce the gender bias by zero editing them. Here are the contributions of our work. And thank you for listening.